Welcome, everyone, to today's episode. We're diving into a topic that has challenged clinicians, scientists, and public health experts for decades: early detection of ovarian cancer. Despite modern imaging, biomarkers, and large scale screening trials, ovarian cancer remains one of the deadliest gynecologic malignancies. Why has early detection failed? And what innovations might finally change things? Let's explore this in depth.
Exactly. Most students learn early on that ovarian cancer has a poor prognosis because it's typically diagnosed at an advanced stage. But what's far less appreciated is why this happens, and why even the most ambitious screening programs have failed to reduce mortality. So today we're unpacking the biology of the disease, the limits of current tools like ultrasound and CA-125, and emerging technologies from AI to nanotechnology, offering hope for the future.
Let's start with the basics. The most common subtype, high-grade serous ovarian cancer, or HGSOC, actually doesn't start in the ovary. It begins in the fimbrial end of the fallopian tube in tiny microscopic lesions known as S-tick lesions, serous tubal intraepithelial carcinomas. These lesions are extremely small, often only a few millimeters, and completely invisible on imaging, but they exfoliate cancerous cells into the peritoneal cavity very early, allowing the disease to spread long before a mass becomes visible.
And the next key point is growth speed. Recent growth kinetics studies show that HGSOC lesions double in volume every 1.8 to 2.2 months. That's incredibly fast compared to many other solid tumors. For context, a lesion in the pelvis takes about 2.2 months to double, and an omental lesion about 1.8 months. Not surprisingly, these tumors metastasize early, on average just 13 months after initiation. By the time a tumor is detectable on ultrasound or causes a rise in CA-125, it may already be widely disseminated.
Given this biology, it makes sense that screening struggles. But we have hard evidence, too. Let's take the two major trials that shaped global guidelines: PLCO in the United States and UKC TOX in the United Kingdom. Both tested combinations of transvaginal ultrasound and CA-125, including advanced algorithms like ROCA. And guess what? Both trials showed no reduction in ovarian cancer mortality. Some women were diagnosed slightly earlier, but not early enough to make a survival difference. Tumors were already biologically advanced, even when radiologically early.
And it wasn't just that screening didn't help, it actually harmed many women. PLCO showed that false positive ultrasound results led to unnecessary surgeries, anxiety, and complications. Because CA-125 is not specific, it rises in benign conditions like endometriosis, fibroids, or even infections. And when you use a non-specific test in a low-prevalence population, false positives inevitably overshadow any true positives. So major organizations from ESGO, ESMO, and ESP to the USPSTF now agree: no screening for average-risk asymptomatic women.
Let's break down why these tools fail. Transvaginal ultrasound is excellent for characterizing a known adnexal mass, especially in expert hands, but it cannot detect microscopic or flat lesions, which is exactly how HGSOC begins. Ultrasound is also operator dependent. A recent study showed that examiners perform extremely well in the pelvis, but accuracy drops significantly in the upper abdomen, where peritoneal and diaphragmatic disease often hides.
And CA-125 has its own issues. It's not elevated in all ovarian cancers. It's elevated in several benign conditions. It fluctuates with menstruation and inflammation. Even the ROCA algorithm, which interprets CA-125 transdynamically, failed to reduce mortality in UKC tox. The real problem is that both CA-125 and ultrasound detect disease too late, because the true early phase is biologically silent and invisible.
Now let's switch to innovations. One breakthrough is AI-enhanced ultrasound interpretation. In a major international multi-center study, transformer-based AI models trained on more than 17,000 images outperformed both expert and non-expert sonographers. Across all diagnostic metrics, sensitivity, specificity, accuracy, F1 score, the AI models did better. Even more impressive, AI performed consistently across 20 centers, 8 countries, and multiple ultrasound systems.
And the impact goes beyond accuracy. A simulated triage model showed that using AI could reduce referrals to expert sonographers by 63%, while improving diagnostic performance overall. That's huge, especially in regions lacking specialized expertise. But as powerful as AI is, remember, AI improves diagnosis of visible lesions. It does not solve the biological barrier of preclinical disease. It makes clinicians better, but it cannot detect what is not yet detectable.
Next up, biomarkers and liquid biopsy. Researchers are exploring circulating tumor DNA, microRNAs, exosomes, and multi-protein signatures. The idea is appealing. Detect molecular signals before tumors are visible. However, early HGSOC sheds very little material into the bloodstream, so current liquid biopsy methods aren't sensitive enough for true early detection. Future approaches may combine cfDNA with nanoparticle-based capture technologies to improve sensitivity.
And what about beta-galactosidase? This enzyme is overexpressed in ovarian cancer cells and is emerging as a potential biomarker and molecular target. This sets the stage for nanotechnologies, which brings us to one of the most exciting research areas.
Nanotechnology can detect incredibly small amounts of biomolecules, sometimes at levels traditional assays can't even measure. Many nano-based biosensors achieve greater than 90% sensitivity in experimental models of early-stage disease. But the real revolution comes from AI-EGENs, or aggregation-induced emission molecules. These fluorophores stay dim in solution but become brightly fluorescent when aggregated. It's a perfect property for biosensing and imaging.
One standout example is TPAG, a water-soluble AIE gen. It has two remarkable properties. One, it detects salivary alpha amylase at extremely low levels. LOD is 0.004794 U per ml. That's far more sensitive than conventional kits. And two, it targets ovarian cancer cells by binding beta-galactosidase, which they overexpress. This enables rapid fluorescence imaging and opens the door to theranostics, imaging plus phototherapy combined. These technologies could eventually provide cheap, minimally invasive, high-sensitivity diagnostics, but they still require large-scale clinical validation.
Considering all this, what might future early detection look like? It won't be annual ultrasound, it won't be isolated CA-125 tests, and it won't be a single magic biomarker. The future likely lies in multimodal, continuous biological monitoring combining AI-enhanced imaging, nanobiosensors, liquid biopsy, molecular signatures, and risk-stratified screening in high-risk groups. This integrated approach could finally widen the detection window beyond the current 4 months.
Until then, clinicians must focus on rapid evaluation of symptoms, high-quality diagnostic imaging, appropriate triage to specialists, avoiding false positive harms, and educating patients on realistic expectations. For the foreseeable future, early detection depends not on screening, but on better diagnosis and technological innovation.
So, to wrap up, ovarian cancer's biology, not our technology, is the main reason screening fails. Rapid growth, early dissemination, and silent progression make traditional methods ineffective. But the horizon looks promising. AI, nanotechnology, and molecular innovations may transform detection over the next decade.
Exactly. The key is integration. combining expertise, imaging, AI, and biology-driven tools. While we're not there yet, the field is advancing rapidly, and future clinicians will likely practice in a completely new diagnostic landscape. Thanks for listening, and stay curious.